we are taking a look at polynomials. We have three goals with polynomials. First, we want to be able to identify which functions are polynomial functions. Second, we want to be able to create the graph of the polynomial function. And third, we want to be able to connect key features of the polynomial to its graph. To get started, we'll look at identifying polynomials. By definition, a polynomial is the sum of one or more power functions, where each power is a non-negative whole number. If you think back to our lesson on power functions, in power functions we knew what the power or exponent was. In power functions, there was no plus or minus, so the polynomial differs in that it's the sum, so there are multiple terms within the polynomial, whereas the power function had just one term. Also in the power function, the exponent could be positive, negative, or a decimal. Here, we are limiting the exponents to non-negative whole numbers. Each polynomial is then classified by its degree because the degree determines a lot of the key features of the graph, and the degree is the highest power used in the polynomial. So let's take a look at a number of examples and try to apply both the definition and then figure out the degree for each equation. As I look at the first example, I look at the exponent. The only exponent is the unwritten 1 that is on the x. 1 is a non-negative whole number, and so this is a polynomial. So is it a polynomial? The answer is yes. And then what is the degree? The degree is 1. And we have a name for them. This is linear. And so we could make a conclusion. This conclusion is that all linear functions are polynomials. And we studied them as a separate group because the degree of 1 on the variable having an exponent of 1 groups them together. And so we studied key features of them earlier in the course. The second one, as I look at this equation, I see that the exponent is t. So is it a polynomial? No, it is not, because exponent is a variable. Specifically, this equation fits the NPAT formula. So in this equation, we have n equals starting amount of 10. We have a growth equation with that growth factor of 1.33 to the x. And exponential will never be polynomial. Looking at number 3, the exponents here on the variable are the 2 and the unwritten 1. Both of these are non-negative whole numbers. So yes, this is a polynomial. The degree is 2. The name is quadratic. And again, we studied them as a separate grouping because all of the quadratics take on certain key characteristics. And so again, we can make a conclusion here that quadratics are always polynomials. Example 4. This is not a polynomial. And the reason why is because of the square root over x. If the square root was just on a number, it would still be a polynomial because it would just be an irrational number. But with the square root over the x, we had talked about, when we talked about power functions, that the square root is really a decimal exponent. And so this function could be written as y equals the quantity x plus 7 to the 0.5 power. And so then this exponent is not a whole number. Functions where there is any root, square root or otherwise, over the x will not be polynomials. Number 5, this one is not a polynomial. And this one, both of our exponents are not whole numbers. So the reason why exponents are not whole numbers. Our final one, this one is not. This one, the explanation is a little bit harder to explain, but I think you will see it. The true reason that we have this as not is because there is division by a variable. And whenever there is division by a variable, it is not a polynomial. The reasoning behind that explanation, this function could be written as 5x squared plus 2 times the quantity 4x minus 1 to the negative 1 exponent, because the negative exponent would move that quantity to the denominator. And so this presents us a problem when we're talking polynomials, because our definition said it had to be non-negative. And so our issue with division is that all division is a negative exponent. Now, it's fine to have division as part of the coefficients, but the key is we may not have division by a variable, because then we have a negative exponent on that variable. This type of function, where we have a fraction of two polynomials, is called a rational function. We'll study them this week in the second half of class, and kind of like exponentials, they will never be polynomial. So once we identify a function as a rational function, it will be taking on different characteristics than a polynomial function. So let's look at another list, some additional examples. What I would love for you to do is to stop the video and answer these for yourself, and then come back and check your work. I'm going to quickly go through answers. I am going to add some vocab as I go through answers. So even if you're feeling confident on the answers, do continue the video to get the additional vocab. Number 1 is yes. When I look at the exponents, all of the exponents, including the unwritten one, are non-negative whole numbers. The degree here is 3. And the name for that is cubic. And we are going to be studying cubic as a grouping of polynomials. The fact that there's a square root over the 2 is not an issue. It just means that the coefficient is irrational, but it does not impact the exponent. Number 8, when I look at the exponents here, they are all non-negative whole numbers. So this one is yes. Degree is 4. And the name for that is quartic. And again, that is a vocab word that you want to associate with degree 4. Number 9 is no. And there are 2 reasons. There is division by a variable. and the variable is the exponent, or the exponent is the variable. So it's not locked in as a non-negative whole number. Number 10 is yes. Degree is 3, and again, that vocab word is cubic. Number 11, looking at all of the exponents here, all of the exponents are non-negative whole numbers, so that is a clear yes. Degree is 4, because that is the highest exponent, and again, the naming of this one is quartic. And finally, this one is no, and the rationale is because there's a variable in the root. This is a cube root, which would be a fractional exponent of 1/3, and so that is not a whole number, and so we cannot include that in our definition of polynomial.